Yeah, comes on everyone. Let's start off. So last thing that we started with the power produced in a resistor, and we did a problem based on thermodynamics here. I square R. Great. Let's go ahead. So we got a container here filled with some amount of water. Then what you did, you took two resistors, you kept them in parallel, R1, R2, and you connected this with a battery of voltage V. Then you took resistors R1, R2, then you connected a battery like this with a voltage V. So you kept them in series and here you kept them in parallel. So these are identical containers with the same amount of water. So when you kept them in parallel, it took 10 minutes to boil the whole water. When you kept them in series, it took 40 minutes to boil the water. Find R1 by R2. So same battery, the resistors when they're kept in parallel and they kept in series, so they produce heat and that heat is used to boil the water. Assuming everything else is same, find the ratio of R1 by R2 if the time taken is 10 and 40 minutes. That's an easy question. It's based on calorimetry. Any answers? So we do have some answers. Yeah, right, Param. Right, Samyak. So let's see. So the water is same, so the amount of heat required will be same. The heat generated must be same. So in the first case, heat generated is V square by R equivalent. R equivalent is R1, R2 by R1 plus R2. Remember, we'll use V square by R because the battery is same. Don't use current because current will change. And time is how much? 10 minutes. This must be equal to V square by R equivalent, which is R1 plus R2. And what is the time? 40 minutes. So that's your power into time. That's your heat produced. Solve this, you will end up with R1 is equal to R2. 1:1. So both the rest are equal. Clear with this. So it's like straightforward one step question. So clear? Next thing. You can simplify that. V square will cancel R1 plus R2 whole square. You'll get R1 minus R2 whole square is equal to 0. You'll get R1 is equal to R2. They can change numbers and you'll get some other ratio. Next thing, bulbs. If you ever go to a shop and get a bulb, right? And when you ask him, give me a bulb, what is the first thing they'll ask you? They'll ask you what wattage you want, right? So when you go for a bulb or anything, right, there is always something called a rated voltage. So this is what you'll see on a bulb. So on a bulb, right, it will be written something like this: 220 volt, comma 4 watts. Now understand the meaning of this. The meaning of this statement is if we give 220 volts, right, then we get 4 watts of power. That is the meaning of that symbol. It does not mean it will work only at 220, right? It does not mean anything. It simply says if you give 220, you'll get 4 watts of power. And that's because our voltage supply in the house is always 220. So when you go to a shop and ask them, give me a bulb of 10 watts, he won't ask you what is the voltage. It is assumed it is 220, right? So indirectly, what you get from here, power is V square by R. So indirectly, this is a way to get resistance. So resistance of a bulb is rated voltage by rated power, right? So be careful here. V is the rated voltage. It's not the voltage that you apply. So just to give an idea, so if you buy a bulb in India, right? Let's say it is 220 volt and 4 watt ka rated, and you go to US and put this bulb there. If you see US ka voltage is 110 volts. So here the power would be this thing. So first of all, the resistance of the bulb will be 220 volt ka square by 4. Now if you take this bulb and keep it in the 110 ka socket, the power is V square by R bulb. Now V square is 110 square by 220 square by 4. This comes out to be 1 watt. You get the meaning of this? So if you take a bulb in India, which says 4 watt, if you go to US and use that same bulb, you actually get only 1/4 of the power. That's because their voltage sources are at a low voltage. And that's one of the problem they have actually. Because the voltage is less, they actually have to consume, the devices and everything are manufactured for 110 volts. So they have to get more current in order to do this. If you take more current, you actually get more losses. So US ka electricity grid is inefficient. But in the beginning, they started with 110 and it was too expensive to change the whole grid. So they're still sticking to it. So 220 is what we use. So this is the meaning of this. It does not mean you cannot use the bulb at 110. It does not mean you cannot use the bulb at 440. You can use the bulb at whatever voltage you want. Everyone clear with the meaning of rated voltage and rated power? So the meaning of that is if you put 220, you get 4. That's it. It means that. It does not mean wo har bar 4 dega or you have to keep only 220. So let's see a question based on that. So let's say we have two bulbs, 220 volt, 4 watt, 220 volt, 2 watt. So this is bulb A and bulb B. Find the ratio of power A and power B. Simple question. Which bulb will glow brighter? Remember, when they ask you ratio, we actually don't need the exact power. We just want a ratio. So you need not calculate the exact value there. First, let's find the distance of the bulb. Let me show you one. So RA will be 220 square by 4. I'll call it R for convenience. So resistance of B is 220 whole square by 2. So this will be 2R. So these things can be treated simply as two resistors. So this is R and this is 2R. So a bulb is nothing but a resistor. And now since both are in series, they will have same current. So power NA is to power NB will be, like I said, you don't want the exact values, you want only the ratio. I square 2R. So you need not even calculate the value of the current, 1 is to 2. So bulb B will glow 2 times brighter than bulb B. Bulb A. Clear with this? So B glows brighter than A. Now, be careful. This does not mean the bulb, this is giving you 2 watts. This does not mean it is giving you 4 watts. Remember, this is the rated voltages. Meaning, if you apply 220, I would give you 2 and 4. But when you're keeping in series, the voltage will divide. So there is no guarantee you're applying 220 across them. All clear with this? Let me give you one more on this. So that word can be misleading. When they say bulb of 4 watts, it does not mean you'll always get 4 watts. B, C, and D. 220 volt, 4 watts. 220 volt, 4 watts. 220 volt, 4 watts. 220 volt, 2 watt. There are 4 bulbs. So they can ask you, arrange the order in which the brightest to dim. So simple question, find the ratio of power. Find power in bulb A is to power in bulb B is to power in bulb C is to power in bulb D. Okay, let's see if Param got something. Anyone else? Now here I can add you one more question actually. If bulb C is fused, matlab it got short circuited. If bulb C gets burned, matlab that filament got burned, meaning it's called open circuit. So you can just, that circuit won't work anymore. What happens to brightness of bulb A and C? So if you see, right, inside the bulb now, you actually have a filament. So the current is coming here, going through the filament and comes back from here. So if the filament gets burned, the circuit actually gets disconnected. So it becomes like this. So there is nothing to connect the circuit. So current will stop flowing in that branch. That is one of the reasons why you don't keep bulbs in series. Even if one bulb goes off, the whole thing goes off. In your house, all the lights and fans that you have, or ACs are connected in parallel. So even if your tubelet goes off, your AC is unaffected. Right, some Param got the same thing, so you might be right. Trishi, look at the last one. Ashita got the same. Utsa got the same. Arya, yeah, looks same. What about the second part? What happens if the bulb C gets burned? What happens to brightness of A and B? Options will be brightness will increase, brightness will decrease, it remains same. So options hoga. Let's see the first part. First, let's get the resistance of the bulb. So resistance of RA will be 220 square by 4. Let's call this thing R. You can clearly see RB is also R, RC is also R. RD will be 220 square by 2. So this is 2R. So I can replace this whole circuit with resistors. R, 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 and 2R. Now, like I said, you don't need to know the exact values. Let the current from the battery be I. This is I, this is R, and that is 3R. So current will divide in the ratio of opposite resistance 3:1. So in this branch, you'll have current 3I by 4. And in this branch, you'll have a current I by 4. Is that clear? You don't need to know the exact value of I, you just need the ratio there. So power of A is to power of B, power of C, and power of D. This ratio is simply the current, I square R. Current in B will be 3I by 4 whole square R. Power in C is I by 4 whole square R. I by 4 whole square 2R. I square goes off everywhere. This will be 16 is to 9 is to 1 is to 2. That's your answer. So A is the brightest, then B, then D, and then C is the last. All clear with this? There. So bulbs are simply convert them into resistors, right? In they're asking who is bright, it doesn't really matter what is the initial current. So you can take I and split them. Hope the first part was clear. Okay, let's see the second part also. Now, what happens if the bulb C gets fused? So if the bulb C gets fused, how the circuit will look like? So you can just remove this branch here. So this is useless. This is how it looks. So C is gone. So this circuit is disconnected. It doesn't work. Now you have to be careful here. So how will the new circuit look like? So I'll just draw a new one. Let's see. So here you are comparing what happens to the brightness of A, meaning you're comparing A ka initial brightness to the final brightness. So initially, this is how the circuit was. This is V, R, 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 and 2R. We can clearly see here R equivalent will be, this is 3R and this is R. So that will be 3R by 4, 3R by 4 plus R. Yeah, that's 7R by 4. That's your R equivalent. So current I1 will be 4V by 7R. So initially, this is the current which is flowing I1. And here the current will be 3I1 by 4. And this was I1 by 4. This is important. The resistance of the circuit itself will change. So the current also will change. Now when the bulb C gets fused, bulb C is burned. So you can just remove from the circuit. Now the new circuit will look like this. This is R and this is R. Now the current in the circuit itself will change. Now this current is I2. All the current will flow here. So I2 will be V by 2R. Now look at this thing. So now when I talk about bulb A, what was the initial power of the bulb A? So we are doing before and after. So initially the power was I1 square R. Now the power was I2 square R. R is anyway same. This will be 16 V square by 49 is to, this is 1 by 4 V square. That R will cancel anyway. V square will cancel, R will cancel. This will be 64 is to 49. So this is the ratio of the brightness. So the bulb wake up brightness has decreased. Initially it was 64, now it is 49, whatever it is, that ratio. Same thing if you do for B. So when you say whether the brightness increased or decreased, you are comparing it with the same bulb initial and after. Here the current will be 3 I1 by 4 whole square R, I2 square R goes off anyway. This would be 9 by 4 and I1 square will be 16 by 49. I2 is 1 by 4. So this will be what? 4. 4 will cancel. 69. This will be 144 is 249. Both of them will become dim. Clear with this? Bulb D won't work only. Bulb C anyway is gone. Check the calculations. I hope I didn't goof up anywhere. I goofed up here. This is 9 by 16. So 16 will cancel. This will be 36 is to 49. Yeah. B is actually becoming brighter. Are you clear how to check this? So if they say something like this is becoming brighter or dim, you have to compare it with the initial. So B becomes brighter. A actually becomes dim. It's compared to previously. You're not comparing A and B, you're comparing A with previous and right now. Is this clear, everyone, how to play with this thing? So there are two ways you can ask. I can give you bulbs and ask you compare between the bulbs, or I can compare the same bulb before and after. So clear? Any doubts on this? Sudiksha, Tanshika, Kanishka, clear with this? Vedika, Shreyansh, clear? Shreyan, Akanksha, Naisha, got this? Next one. Bulbs in series. What happens if you keep bulbs in series? Let's say you take a lot of bulbs and you keep all of them in series. Let the power be P1, P2, and Pn. Remember, all these are rated powers. So we know resistance is equal to V square by P. This is your rated voltage. This is your rated power, meaning if you apply the 220, you would get a P. And let's say this is the whole thing is connected to V, which is your rated voltage, let's say 220 or whatever. Now, if you look at this, indirectly the bulb is nothing but a resistance. We can write this R equivalent is nothing but R1 plus R2 plus so on till Rn. Then this R equivalent is nothing but you can clearly see R is proportional to 1 by power, the rated power. So this will give you 1 by the equivalent power or the total power is 1 by P1 plus 1 by P2 plus so on till 1 by Pn. It will behave like capacitors, opposite of this. So example question would be something like this. We have two bulbs, you place them in series with a rated voltage 220. So let's say this is 220, 4 watts, and this is 220, 2 watts. Meaning if you had connected each of them individually, you would have got 4 and you would have got 2. But when you kept them in series, the new power you will get is this. So 1 by power will be 1 by 4 plus 1 by 2. So now the power of the system, the total power, that would be 4 by 3 watts. You get the meaning of this? So if you take these bulbs and connect across one source of 220, you actually get less power than both of them. So you would get questions of this sort. So two bulbs of 4 and 2 are connected in series and connected to the voltage. What is the total power of the system? It's not 4, it is not 2. Most people think it is 4 plus 2. You have to be careful there. It would be 4 plus 2 if both had same voltage 220. Because you kept in series, the voltage across them will be dropping. So you won't get the rated voltage across them. Clear with the example? So there, this has bulbs in series. The power will be like capacitors ka formula. Till now, if you see, right, we have seen how many things till now. We have seen springs in series and parallel. Then we saw capacitors. Then we saw resistors. Then we saw thermal resistance in heat transfer. Then we saw, this thing, viscosity may the resistance to fluid flow. So 5 times we have seen already the series parallel stuff. The next thing, bulbs in parallel. This was easy. Since all are in parallel, all have same voltage. The total power would be P1 plus P2 plus so on till Pn. They directly add up. So because here the formula was reversed, no? 1 by R equivalent will be 1 by R1 plus 1 by R2. So on till 1 by Rn. And we saw power is proportional to 1 by R. So you can just add it up. So if you keep bulbs in parallel, the power simply adds up. If you keep bulbs in series, the power actually drops. I have no idea, Srihari, where you learned it. I
सर
don't know which chapter you
इंडक्टर
learned.
और कैपेसिटर का पावर लेते हैं सर। सर तो हम
Yeah?
लोग सर तो उसमें सर दी रेजिस्टर इज द आउटसोर्स जिससे पावर इज डिसिपेटेड।
Yeah, what are you talking about? Which chapter are you talking about?
सर एसी करंट में।
AC current, where did we do it yet? You finished already?
वी हैव नॉट डन सर, बट इज
Then
दैट अ
ignore it.
सिमिलर
No,
केस?
no, it is not similar.
तो
Don't mix it up. It's something else completely. Don't mix it up. It has nothing to do with this. Clear with this? Bulbs in parallel. So this is all we are doing DC only. AC का देखते हैं बाद में. There's nothing like what you're saying. See, current doesn't care whether it is AC or DC. So it works. So that's a little about bulbs. So be careful. The most important word is the rated voltage and power. When people see 224, they think like it will work only at 220, or they will think it will always give 4 watts. Not necessary. That is simply telling you if you give me 220, I would give you 4. The next thing, maximum power transfer theorem. Now, if you remember in the beginning, we saw a non-ideal battery will always have an internal resistance. That means when you are trying to extract power from a battery, whether you like it or not, the internal resistance will always dissipate some energy. So you're actually always losing some energy. So then the question is, what is the best you can do? What is the maximum power you can extract? So if you have a battery, E and R, and if you connect to an external resistance, R, so this whole red thing here is a battery. You cannot separate it. So the question is, what should be the value of capital R? That is what you can change. You cannot do anything to the small r. That is fixed. So what value of capital R should I keep so that I can get maximum power from the system? So small r is your internal resistance. R is your variable external resistance. So capital R is the value which you can change. So let the current in the thing be I, right? And here, if you see, all energy that you produce in small r is wasted. You cannot recover it. Battery becomes hot. That's what you will see when you're charging your mobile phone. It does get hot. So current I in the circuit is E by R plus R. The two resistors are in series. So power in capital R is simply the current I square R, which is E square by R plus R whole square into R. We have to do maximum minimum. So dP by dR is equal to 0. When you do this, you end up with R is equal to small r. So there. So you get maximum power when the internal resistance is equal to external resistance. So when R is equal to R, when the external resistance is equal to internal resistance, we get max power in external resistance. So then look at the irony of the situation. That means no matter what you try to do, there is no way you can get more than 50% power there. The internal resistance will always eat away half of your power. And this is the reason, right? If you try to put a battery system in the house, just imagine what would happen. In an ideal case, every time you try to charge the battery, you lose 50%. Every time you try to recover the energy from the battery, you lose another 50%. So if you put 100 watts, in reality, you get only 25 watts in the end. So storing power is actually pretty, inefficient in that way. So all this solar power that we are generating, right, during daytime, India has this problem now. We are actually generating enough renewable energy, solar and wind, but we don't have a proper transmission lines because most of this power is being generated in deserts. I think last month there was an article like we produced almost 25 to 30 gigawatts of power, and there was no way to send all the power into the grid, and all that power was wasted. The 25 gigawatts is something like what? I think total power ka India consumption is around 300 gigawatts. That's 10% of the country ka supply. You just wasted it because we couldn't store it, we couldn't send it into the grid. So now they're trying to do something like that. They're trying to put this, big battery systems which can store power for 4 or 5 hours or something. But this is the problem. You know what Adani does? So battery system, this is pretty inefficient, right? So what happens, right? This solar power during daytime, peak 12 o'clock, 1 o'clock, it produces maximum power. They have huge facilities. Adani is building in Rajasthan one of the biggest, the solar thing. The size is 5 times the size of Paris. That entire plant is the size of 5 times the city of Paris. You stand there with the binoculars, you can't even see the edge of that setup, meaning it's just so huge. That whole setup produces 30 gigawatts, 1/10 of the country ka power supply. Right? So they're making something like that. And now what they're doing right now, right? During daytime at 12 o'clock, solar power is being produced at such a high rate, it's pretty cheap. It becomes something like 1 rupee. But during evenings, when the power supply starts going down during night, you can sell the same power at 10 rupees. Now see what happens. That means even if I store 100 watts, right, 100 into 1 is 100 rupees. When I try to extract it back, only 25 will come, but the cost is 10 rupees. So that will be 250 rupees. So I still make profit, isn't it? Even though you lose 75%, you'll make profit because the price has become 10 times more. So yeah, that's the game you play. Anyways, clear with this? Yeah, you can do that. You can put power in the house and all, but Mumbai में इतना place कहाँ पे है to put a solar panel? And ऊपर से you have a lot of issues रहे मतलब सबको लगता है solar panel लगाओ हो जाएगा. All you need is one pigeon to come and shit on the solar panel. And pigeon का shit is acidic. It's not a joke. मतलब it looks laughing matter, but that pigeon का shit is acidic. The moment it falls on the solar panel, it gets short circuited and that whole, that solar panel goes off. You have to replace the whole thing. So yeah. Let's see the next one. The best place to put solar panel is on moon. No atmosphere, no dust, no pigeons to shit. Easy maintenance. So we got a battery here. This is 2 ohms. This is 3 ohms, and this is R. This is a transmission. There are ways to do it. You can use wireless transmission for power. You convert that into high frequency signals and transmit to Earth and convert it back. Anyway, listen to this question. Again, this concept is not tough, but this one, right? People get trapped here. So that red thing is your internal resistance. So the first question, find R for max power in 3 ohms. Find R for max power in R. Exam they'll ask you the first question, and people write the answer for the second question. I'm giving you both. So let's see if you can figure out what's the difference. So capital R is the only thing which you can change. So what is the catch? Now see, this is what happens with everyone. People remember this. For maximum power, capital R is equal to small r, right? And then they will say, okay, this is now see, this capital R does not know who is internal resistance. So it will think 2 and 3 is internal. Then they'll think R is equal to 5. Now you have to be careful here. Look at this thing. Look at this statement that we said. When R is equal to small r, that means when your external resistance is equal to internal resistance, you get maximum power in external resistance. We don't know what is the power in some other resistor, but look at this question. Find R to get power in 3. They are not the same thing. You're talking about completely two different things. So how do we solve this? You go back to the basics. What is the current in the circuit? 5 by 5 plus R. So you want power in 3 ohm ka resistor, which is I square into 3, which is 25 by 5 plus R whole square into 3. You can clearly see for maximum power, R must be 0. So it is good if that resistor is not there. It becomes a wire, it will be good. So that's 25 into 3. Is that making sense? Look at the second question. The power in the capital R. This is 5 by 5 plus R whole square into R. Now there is a thing there in the numerator also. 25R by 5 plus R whole square. Now when you do maximum minima here, dP by dR is equal to 0. We get R is equal to 5. Are you getting the difference? So maximum power transfer theorem says the value of R must be equal to internal resistance to get maximum power in R. I hope you're getting it. The second one is maximum power transfer theorem. First one is not a maximum power transfer theorem. It is something else. It has no relation to the maximum power transfer theorem. Is this making sense? So maximum power transfer theorem says to get maximum power in the variable resistor, that variable resistor must be equal to internal resistance. But look at the first question. Find the value of R to get maximum power in some other resistor, 3 ohms. They are not the same. Are you clear with this? Again, not a tough question, but they'll ask you the first question in the exam, and most people blindly write the second one ka answer and come. Because they just remember that one statement. If R is equal to R, power is maximum. Why? No one, they just do it. Clear with this? So maximum power transfer theorem, there's nothing much on that. That's the only idea there. Next thing, fuse. This is a little, this is an old school thing. You guys must not be not even knowing what is a fuse. So fuse, right? Basically, it is a safety device. You must have seen this when you buy this, the switch box or something. Yeah, right now what you use is that, MCBs in the house, which are semiconductor things. अगर घर में कभी कुछ short circuit हो गया, they'll simply trip. You have to just go and put it back up and it works. But when I was in school, things were not like that. There used to be physically a wire. And when a large current flows through this, it literally burns when current flows through it. So a simple fuse, it would look something of this sort. There. You can see this wire here. This is the fuse wire. So you have a small socket kind of thing there, and you keep this the bulb, this cylinder kind of thing in between. So when the power is going through this wire, and let's say if for some reason in the house there's a short circuit and you get a huge current, when the current flows, this wire will get heated up and this wire will melt, wire will get disconnected. So suddenly house ka power supply goes off. So this is how people we used to use before this all these semiconductors. Now it is so easy, like it will just strip and you have to put the switch back. But yeah, when I was in school, though, it used to be a mess. You have to go and get this fuse ka wire and you have to replace this wire and then put it back. It is a lot of work. So the symbol, right, will look something like this, 10 ampere. It will be written like this. So the meaning of this is if the current exceeds 10 amperes, the wire will melt. And circuit gets disconnected. I think I was in fourth or fifth standard. I used to feel like I'm a big scientist. So I used to do all nonsense things in the house. So, and I was always curious about, the plug point, there are three holes there. So what I did one day, I took a tongue cleaner, which is made of metal, and I kept it in this plug point like this. And I switched it on. So what I did literally, when you keep a metal here, resistance is almost zero. So current will be V by R. R is almost zero. You get a huge current. Basically, that's what I mean by short circuit. The power went off in the house. Basically, the fuse wire got melted. Ye pura circuit board, it became black. It got burned inside. Pura, you got all that sparks and all. Don't do this at home. This is really dangerous. Things can go really bad. Right? Power went off. I got really scared. I removed that. My best part, luckily it got disconnected. I took it with the hand and I pulled it out. If the current was still there, I would have got a shock. That's what can happen when you're an idiot. Like, when you're a kid, you really do all these kind of idiotic things. And then I just came out silently and people are wondering what happened, what happened. Even I started acting like, oh, something happened, something happened. That's what you do, right? You do some shit and then you come out and you act like, oh, what happened here? I think that's the first time in my life I heard my mom saying, "Are fuse egripoyindi." So in Telugu, she said fuse egripoyindi. Matlab fuse burned. But in Telugu, right, egripoyindi also means it flew away. You can take it in another different meaning. So here, me being a kid, I was wondering, okay, fuse egripoyindi, matlab fuse flew away. So this is what I started assuming. That means in our meter box, there must be a bird inside which is producing power, which we are using every day. That is what I thought. Power is coming from a bird which is inside the meter box. And because I did this nonsense, the bird got angry and flew away. And now I was wondering how will my mom go and catch that bird? So I don't know what happened. They did replace the wire or something. It won't worked out. But I think for a week I was thinking there's a bird in the, the meter box which is producing power for the house. So yeah, I didn't tell my mom. I didn't tell anyone. After I went to IIT, I think when for holidays I came, I was telling her this story then. And she was like, idiot, you are the one who did all that nonsense. So I felt after I think almost 10, 12 years, that was a safe time to tell. So and I used to be really curious when I was a kid. And those are the times, you didn't have any gaming, internet, YouTube and all. So you do all stupid things to keep yourself entertained. So whenever power used to go off, I used to run onto the terrace and used to look at the vehicles on the road. मेरा यही doubt था. The cars, the lights are on, right? For the headlights are on for a car and a bike. So my doubt was, when the car is going, there should be a wire also behind it, right? Because how will a light glow without a power supply? And if two cars go opposite to each other, the wire should get tangled. So the road should be full of wires. But I never saw a single wire on the road, but all the vehicles are having lights. So I was really confused, where is the power coming from? But that day, the meter box concept, I think it made it clear. Like I was sure in every car, there is a bird which is producing power. So, but that bird is also called as a battery, I think. That's what I realized later on over years. So I had all weird imagination. So I think the most stupid thing I did, I saw an ad one day on the TV, Melody chocolate ka ad tha. So in that, there is a brother and sister. They go to a shop, they buy two chocolates. Both of them put the chocolates in the mouth and they rotate. When they rotate, they get a new dress. Now I wanted to surprise my mom. I went to the shop. I brought two Melody chocolates. I went into the room. I closed it because it was a surprise. I took a Melody chocolate, kept it in the mouth, and I started rotating. I rotated for 3 or 4 times, and I was wondering why there is no new dress. I thought maybe chocolate was defective. That's why I brought two chocolates. Huh? I was smart. Then I got the second one. I tried again 2 times. It didn't work. And after some days, I guess I realized I got fooled. Like whatever they show in the TV, bloody all of it is wrong. Nothing is true actually. See, that is how dumb we used to be. Like, looking at an ad in the TV, I used to think it is true. I used to have very weird confusions. In the movie, the villain used to die, he used to come in second movie. You know what I used to think? Twins. He used to come again in third movie. Triplets. That's the only explanation I had. Like every movie, the villain dies and he comes again. How do you explain that? So yeah. So next time you feel dumb about anything, remember we used to be more dumber than you guys. So yeah, continue working. That is the only thing you can do. Anyways, so getting back to this thing. So this fuse, right? This would be a good theoretical question. Like fuse is made of a material. So what kind of material you want to make the fuse with? Question would be like this. Fuse of made of material, there'll be four options. High melting point, high specific heat. Remember specific heat capacity? Q is equal to ms delta T, that one. So the fuse material, a fuse is made of a material of high melting point, high specific heat capacity, low melting point, low specific heat capacity, high specific heat, low melting, low specific heat, high melting. ऐसा four options बनाएंगे. So what do you guys think? Fuse wire should have high melting point or low melting point. Let's start from there. So ask yourself, घर में short circuit हो गया, large current is flowing. You want the wire to melt fast or slow? You want the wire to melt as fast as possible. So you should have low melting point. Should it have high specific heat capacity or low specific heat capacity? What is specific heat capacity? If you remember, Q is equal to ms delta T. So the change in temperature is proportional to 1 by S, meaning in order to change the temperature, you need to give more heat for the same change in temperature. So higher the specific heat capacity, more difficult to change the temperature. Remember? So now you tell me, there's a big current in the house. You want the wire to melt fast. So should I give less heat to increase the temperature or more heat to increase the temperature? So even for a less heat, I want the temperature to change faster. So low specific heat capacity. So low specific heat capacity meaning the temperature will rise even for a small amount of heat. And if the temperature rises fast enough, it will melt. So both should be low. Are you clear with this? That's your specific heat capacity there. So that's one good theoretical question they're going to ask you. Fuse wire is made of what? Let's say you two brought fuse, 10 ampere ka fuse. 5 ampere ka fuse. You're sending current I, and let's say this is 10 ohms and this is 5 ohms. So what is the maximum current you can send through the circuit without, so that both the fuses are safe? You don't want any fuse to burn. So that both the fuses work. Yeah, this is a very bad way of using a fuse, but let's say someone did it. What is the maximum current you can send in this parallel thing so that both the fuses are safe? Right, Samyak. Try others. Yeah, right, Harshita. Right, Param. Right, Shreyansh. Right, Akansha. See. So one thing is clear: the current doesn't care about the fuse. Current will always divide in the ratio of opposite resistances. So if the current here is I1, here the current is I2. So I1 into 10 ohms is equal to I2 into 5 ohms. The numbers are just matching, but so I1 by I2 is half. So whatever current you send, the current will always go in this ratio. Now, see, there are only two possibilities. Since you want to send maximum current, maybe the 10 amp is taking maximum current or 5 amp is taking maximum current. So if you take I1 is 10 ampere, then I2 will be 20 ampere. So this will not work because I2 will burn. So if I1 is 10 ampere, then I2 must be 20. Not possible. So if I2 was maximum, then I1 is 2.5 ampere. Yeah, this is acceptable. Therefore, maximum I will be 7.5. That's it. That's how you can check. One of them has to be maximum. I1 can't be maximum because the other one will take more current. All clear with this? That's about a fuses. So if you see all small, small things, bulbs, fuse, right? A maximum power transfer theorem, the E heat is I square R. So these are all the small, small things there, but yeah, that's one part of it. The next thing, the important thing, electrical instruments. So listen carefully, they're not tough. As long as you know how it is working, how it is constructed, you'll be able to handle most of it. Now, in electrical instruments, the primary thing you should know is there is actually only one device which is actually there. It's called galvanometer. Later on in magnetism, we will study how it is manufactured and how it works and everything. That itself is another thing. But we have something called a galvanometer. So the main idea here is it is a current sensitive device where the current flowing through it is proportional to the angle deflected. So it is constructed in such a way, the more current it goes, the more it will deflect. So it is a linear function. We will see that construction later on to the angle deflected by the needle. So if you look at the device, it would look something like this. So if you have a current wire, let's say I, so you have readings here, let's say 3 milliamperes, 2 milliamperes, 1 milliampere, 0 milliamperes, 1 milliampere, 2 milliampere, 3 milliampere, something like this. So if the current is going from left to right, then the needle will deflect in this direction. If the current is going to the left side, then the needle will deflect, to the left side. So whichever side it goes, so initially it used to be like this, but now we have better ones. It will always deflect in one direction. But there, so that's what the thing does. So it depends on how you send the current, the needle will deflect in the other direction. If you send the current from here to here, the needle will deflect to the left side. If there is no current, the needle will be straight in the middle, 0 milliamperes. Clear with that? Now, how this is manufactured, don't worry about it. That we have a full thing about it. The symbol for this is G with a circle and around it. This is the thing. That's the symbol for galvanometer, Ig and Rg. So R subscript G is the resistance of the galvanometer. Ig is the current in galvanometer. Now this galvanometer device, right, is very sensitive, meaning you cannot really send too much current. The range will be in the range of microampere to milliampere. So a galvanometer can measure current only in the range of milliamperes. So they cannot withstand large currents. If you send 1 ampere, the whole this galvanometer will burn. Again, the reason is to do with the construction, the way we manufacture it. To make it more sensitive, we use thin wires, and thin wires will burn down easily. So there is something like that. We'll see later on. So they cannot withstand large currents. Right? So it can measure only very small currents. And there is one more word they use, something called full-scale deflection. Matlab, that is your maximum Ig. So if someone says the full-scale deflection is 10 milliamperes, that means this thing can measure maximum current is 10 milliampere that we can measure. So that is another word they'll use, full-scale deflection. So the full-scale deflection of the galvanometer is 5 milliampere, meaning it cannot take more than 5 milliamperes. All clear with this? That's about the galvanometer. So all that you need to know is a galvanometer, when the current flows through it, the needle will deflect. It will show you current. But the problem is this thing cannot measure large currents. It will measure very small currents. That's the biggest problem we have. Now, if you look at your house ka AC, right? Your AC ko upar switch ko upar dekho. It will be written 16 amperes. That AC in your house will take up to like 8 to 10, 12 amperes of current. So you actually take a pretty large amount of currents. So now we have to do something to make this measure large currents. So listen to this thing. So we construct an ammeter. So every device that you know is constructed from galvanometer only. So what is an ammeter? It measures current and is constructed by shunting. This is the word they'll use, shunting. Shunting meaning keeping in parallel. That's the word there. Keeping in parallel. The technical word is shunting. By shunting a small resistance to the galvanometer. Meaning this is how you can read. It measures current and it is constructed by keeping a small resistance in parallel. To the galvanometer. So be careful with that word. There's a new word you are listening, shunting. So they will say, the resistance is shunted. Matlab, you kept something in parallel. The capacitor is shunted with a resistor. The battery is shunted with a capacitor. So when they use the word shunting, meaning they're simply saying it is kept in parallel. So this ammeter must be placed in series. So these are the few things when you use. Because if you keep in series, you'll get the same current. That's what you want to measure. An ideal ammeter will have zero resistance. It behaves like a wire. Now let's see how this works. So you take the galvanometer and you keep a small resistance in parallel like this. Let's call this thing RSH, R shunt. This is RG. And you're sending current I here. So here, this whole setup, the galvanometer and the shunt resistance together, this whole red box is what we call as an ammeter. So this whole red box you're seeing is this. This is the symbol for ammeter. So when the current I is coming here, the galvanometer will take current Ig. The shunt resistance will take the remaining current I minus Ig. Since both of them are in parallel, the voltage must be same. So Ig into Rg must be equal to I minus Ig into R shunt. If you rearrange them, you will end up with capital I is equal to Ig into 1 plus Rg by R shunt. This is your main formula. So this gives you a relation between the current in the galvanometer and the current in the main circuit. So how do we use this? Now we do a small manipulation here. So if you see any device that you have, right, you actually manipulate this to show you something. For example, when you stand on the weighing machine, tell me what does it show you and what does it measure? When you stand on the weighing machine, what does it measure and what does it show you? Does it actually measure your weight or mass? What does the weighing machine measure? So a weighing machine measures normal reaction. It doesn't measure your weight. If you stand on it with your school bag, it does not know what is your weight and what is the weight of the bag. A weighing machine measures normal reaction. But what we do, so when a person is standing on a weighing machine, it's measuring normal reaction, but it shows N by G. So they'll take the normal reaction and divide by gravity. You're getting this way? So what you measure and what you see are two different things. The same way, here what we do, the capital I is Ig into 1 plus Rg into R shunt. This factor is your multiplying factor. And listen to this carefully. This is the main idea there. Example, let me take with an example. Let's say you make this multiplying factor because the Rg, R shunt, you can change them. Whatever values you want, you can keep them. Let's say this value is 1000. So you know the meaning of this? So the meaning of this is, now we will take that galvanometer, which can measure only milliamperes. So 0 milliampere, 1 milliampere, 2 milliampere, and 3 milliampere, and so on. So this is Ig. Now what I am suggesting, we will adjust the values of Rg and Rs, in such a way you'll get 1000. I will erase these numbers, right? And I will say this is capital I. So this will be 0 ampere, this will be 1 ampere, this will be 2 ampere, and this will be 3 ampere. Because there is a relation between them now. We know capital I is 1000 times Ig. Meaning, see what it means. So when the current Ig is 2 milliampere, the galvanometer will always show Ig only. So when the needle is actually pointing towards 2 milliampere, what you did smartly, you erased the 2 milliamperes and you wrote 2 ampere there. So even though it is measuring Ig, it is showing you capital I. Does that make sense? What it is measuring and showing is something. For example, instead of 1000, if this was 500, what do you think you will see? This will be 0, this will be half, this will be 1, this will be 1.5, isn't it? The numbers will change. Depending on what numbers you take, you can change that multiplying factor. So when you send 2 amperes of current, Ig will be 2 milliamperes. So the needle will deflect towards 2 milliamperes. But smartly, you erase the 2 milliampere and you kept 2 ampere there. So the galvanometer measures Ig. It does not know who is capital I. But you made it show capital I. Is this logic making sense? Because the galvanometer cannot measure big currents. It will always measure milliamperes. By keeping a shunt resistance, you let most of the current pass through the shunt resistance. And then you manipulated that whole equation because I know the relation between them. I can manipulate that Rg and Rsh to give a good number, a big one like 1000 or 2000. So I got a relation between capital I and Ig. So whenever it shows IG, I will just have to remove that markings, the old ones, and put a new numbers there. So even though it is actually measuring IG, you're still seeing capital I. Is this logic clear, everyone? This is the whole idea behind an ammeter. Technically, the formula is this only, but why it works is because of this. Anyone not convinced with this or not clear, please ask. This is important. If you understood this, then there's nothing like, yeah, rest of the things will come back to back. But the main idea was this. All clear? Take a break, come back by 9:45. We'll continue from here. We'll see more on this. Any doubt so far? Chalo, come back by 9:45 then. Yeah, let's start off. So that's the main theme there. So since you can manipulate the value of Rg and R shunt, you can get a big multiplying factor. So even though the Ig is small, you're making it show, this big currents. That's one. There is also another advantage. So whenever you're creating this ammeter, right, you have to make sure this R shunt is very small. Three reasons. One, range increases. If you make your R shunt very small, I is equal to Ig 1 plus Rg by R shunt. By making the R shunt very small, you can get big current. So you can measure bigger values. So your range increases. Others do keep your cams on. Second thing, if R shunt is small, max current and max current flow, maximum current will flow through it. And Ig becomes very small. And that's what you want. You don't want to send too much current in the galvanometer because it will burn. So you're actually protecting the galvanometer. Therefore, galvanometer is protected. If you let too much current flow through the galvanometer, it will go off. The third advantage, the error decreases. So even though you think you're measuring current, the very act of measuring something messes up the observation. You must have seen that, right? You and your friend are, or you and your mom, you went to some party. You and your mom are, cribbing about some relative. अरे पता है वो relative बहुत गंदा है, वो idiot, that, this, and the same relative starts passing by. then what happens? Your conversation suddenly changes, right? See, the very act of observing changes the whole observation. So same way, when you try to measure the current, you actually mess up the current. See, imagine you have a battery and a resistor. This is V and this is R. So technically, theoretically, the current I is supposed to be V by R. But you can't measure this. You have to put an ammeter. So you went and you brought an ammeter and you connected this in series. And now what happened? The current itself will change I dash. So we get I dash will be V by R plus resistance of the ammeter. So you actually messed up the current which was supposed to flow. You want to measure V by R, but now you're measuring something else. And the resistance of this ammeter 1 by RA is nothing but 1 by RG plus 1 by R shunt. They're in parallel. So you can't make it 0, but if you make R shunt is small, RA will be small, so error will decrease. So these are the 3 advantages you have. These are the kind of questions they'll ask you in boards. They'll ask you, explain the construction of an ammeter and explain the, the value of shunt resistance, why it should be small or something like that. Therefore, error decreases. There. That thing, right? If you see the very act of observing something messes up the observation, it has something, similar to Heisenberg uncertainty principle. If you try to find the momentum, you will lose the position. You want to get the position, you lose the momentum. You can't get both. Yeah, not exactly the same, but looks similar, something like that. Everyone is clear about the ammeter? This is how you construct a galvanometer which can measure small currents. You made it measure big currents now. The next device is voltmeter. Now you want to measure voltage, but remember the only device you have is galvanometer. Now this galvanometer you have to make it measure volts now. Voltmeter. So this thing measures voltage. And is constructed by keeping a large resistance in series. To galvanometer. Voltmeter is placed in parallel. So whichever device you want to measure the voltage, keep it in parallel. So you get the same voltage. Ideal voltmeter has infinite resistance. So this is R. This is your galvanometer. And this is your R large. And then you connect like this. So this whole package here, so galvanometer plus this large together, this is your voltmeter. And this is how the thing will look like. The symbol is V with a circle. That's your voltmeter there. So if you open a voltmeter, you will see a galvanometer inside with a large resistance. So this is capital I. This is actually, the formula is pretty easy. This is IG. So the voltage across R is simply the current into the resistance of the galvanometer and the large resistance. So voltage across R is Ig into Rg plus RL. Bus, that's a direct formula there. So V is equal to Ig, resistance of the galvanometer, plus that large resistance. This is your multiplying factor. Then what we do? We do the same manipulation again. So you'll take the ammeter. Let's say, example, the multiplying factor is large, like Rg plus RL is 10,000. You take a large resistance. So your ammeter, which is supposed to measure current, 0 milliampere, 1 milliampere, 2 milliampere. Now, when you multiply Rg plus RL into 10,000, so this will be 0 volt, this will be 10 volt, this will be 20 volt. So when you apply 20 volts ka voltage, you will get 2 milliamperes ka current. So the galvanometer will measure Ig 2 milliamperes. But what you did smartly, that 2 milliampere will correspond to 20 volts. You got it? What we did again? We manipulated the same thing again. So you're measuring Ig, but now you're showing voltage. Is this making sense, everyone? This is the theme there basically. The galvanometer can measure only Ig, but somehow you have to make it show something else. Any doubts on this? So these are the two formulas you have. Current, capital I. So this capital I is the current in the device which you want to measure. Ig is the current in the galvanometer, maximum which you can send. There's a relation between them. So you can note down the formulas you need. We are going to do problems on that. The capital I is Ig into 1 plus Rg by R shunt. So know the formula and understand how it is manufactured. That is important because if someone changes something, you should know where to change it. And then the voltage the voltmeter is V is equal to Ig into Rg plus RL. And R large must be really big. Same reasons. One, range increases. You can measure bigger values. Ig decreases because the distance is large, very less current will flow through that junction. So your galvanometer is protected. Error decreases. So the same reasons what you had for ammeter. So the idea is the same. So clear with this? Great. Let's see some questions on this. So like I said, there are total 4 devices. So ammeter, voltmeter, then we have meter bridge, then we have potentiometer. So we will deal with these things today. Get them. 38 A, I'll keep all of them together. Again, don't think too much. Most of the it's just simply resistors in series and parallel if you actually see fundamental. But anyway, give it a try. The first one was pretty straightforward. If you see that the current is equal I by 2, I by 2. If the current is equal, then the resistance also must be same. So I by 2 into 20 must be equal to I by 2 into Rg. Therefore, Rg is equal to, there's nothing there. Like I said, simple series parallel. So look at this one. A galvanometer has a resistance of 20 ohms. It reads a full scale. Full scale matlab maximum Ig. Meaning the needle will deflect maximum when you apply 0.2 volts. If you want to convert this into a 10 ampere ka ammeter, the galvanometer coil should have, read the option. The galvanometer coil should have 0.01 resistor in series. It should have 0.02 in series, 200 in series, 2000 in series. So across it matlab shunting. Right, Arshita. Think for a minute. I'll show you. The language is a little weird, but that is how they'll ask you. Let's see. So let's go step by step. Read what he's saying. A galvanometer has resistance 20 ohms. So he gave you indirectly Rg is 20 ohms. Great. He's saying it will become full scale when you apply 0.2 volts. That means if you apply 0.2 volts across the galvanometer, it will show you full reading. So Ig will be 0.2 by Rg, which is 0.01 ampere. So indirectly, he's telling you the maximum current you can have in the galvanometer is 0.01 ampere or 10 milliamperes. That's the first part of the question. You have to get Ig value. Now coming back to the ammeter. So for an ammeter, capital I is equal to Ig into 1 plus Rg plus R shunt. You want to measure how much? You want to measure 10 ampere ka current. So that is your capital I. What is our Ig? 0.01. What is Rg? 20. What is R shunt? This is R shunt. So that will be how much? That is 1000. So R shunt will be 20 by 999, which you can make it 1000 approximately. This will be 0.02 ohms, and it should be in parallel. So 0.02 ohms across it. Are you clear with the question? So ammeter, voltmeter, right? The questions are not tough, but you should see like 10 to 12 models. If you see, you'll get the hang of it. The wordings, you have to be careful. All clear with this? Let's see a few more. Now here, if you see, right, this is a very good one. It's not a tough one, but this is the kind of question they'll make an advanced paragraph. This is a galvanometer whose range can change by keeping different terminals. So just to give an idea here, see what is happening. He's saying if I use A and B terminals, what happens? If I use A and B terminals, means you're going to let the current flow from here. So this would be your Ig, this would be your Ig, this would be your Ig, right? And this would be your I minus Ig. Meaning, if you look at the circuit, right, if you ask the circuit, this is what it will think. I'll just read out the circuit for you, see. So we have that galvanometer. This is how it would look. So this is A, this is B. The galvanometer has 9 ohm resistance, and that 0.9 also will go here. Right? And this is your so this is your 9 ohm and 0.9, and this is 0.1. This is how the circuit will look like. So now you tell me, what is RG exactly here? So even though RG is 9, the circuit will think this whole thing is RG, isn't it? So if you add a resistor in series to the galvanometer, that will go into RG. So here, R shunt is 0.1 and RG is 9.9. Are you clear with this? Suppose if I connect the battery between A and C, can you tell me what is R shunt and what is RG? If you connect it between A and C, then RG will be 9, R shunt will be 0.1 plus 0.9, isn't it? You're getting the catch? Depending on where you keep the terminal, RG and R shunt will keep changing. What if I connect it between B and C? If you connect between B and C, then this will be one resistor, 9.1, that is RG, and R shunt will be 0.9. Is that making sense? So depending on which two terminals you connect, you will get different range of the ammeter there. So and then so here RG will be 9 plus 0.9 ohms is RG. Because see, the equation does not know who is exactly RG. It will think the all resistance here is RG. And then you're done. So capital I is equal to IG plus 1 plus RG by R shunt. That's it. That is the main thing in the question. Depending on which two terminals you take, you can RG and R shunt will change. You want to measure how much? That is not given. IG is 10 milliampere, that is 0.01. RG is 9.9 and R shunt is 0.1, that's 1 ampere. Are you clear with this? Again, if you see, we are still playing with the same formula there. The only difference is what is RG, what is R shunt. RG is not actually resistance of the galvanometer. It is a total resistance with the galvanometer. Are you clear with this? So this is how you can manipulate RG and R shunt. Any doubts on this? Clear now, Vanshika? Trishi? Harshita? Tatyasha? Aditi? Clear? Ovia? Got this? Let's see a few more. There are only two formulas I taught you. You're just playing with that. You need to know the construction and the formulas. A galvanometer coil has 90 ohms. Again, galvanometer coil. So he's talking, this is RG. Has a full scale deflection of 10 milliamperes. So this is IG. A 910 ohm is connected in series. This is R large. You keep that R large in series. With the galvanometer to make a voltmeter. If the least count of the voltmeter is 0.1, what is the least count? The smallest measurement you can make. So when you take your centimeter scale, the smallest measurement is 1 millimeter. So the smallest measurement you can make is 0.1 volt. Matlab, on this device, each division is 0.1. Then he is asking how many divisions are there. Yeah, that's how you pull the data from there. So yeah, most of you got it. So let's see the D part. What is the formula? V is equal to IG RL plus RG. IG is 10 milliampere, 0.01. RL is 910. RG is 90. That would be 10. So this voltmeter can measure 10 volts. So number of divisions is the voltage, which is 10, and each division is 0.1. That will give you 100 divisions. So C is the answer. Clear that voltmeter can measure 10 volts, and you're saying each division is 0.1. So let's see the next one. Yeah, I think most of you are getting it. Okay, let's see the next one. So E part, he's saying the resistance of a voltmeter is 10,000 ohms and the ammeter is 20 ohm. The ammeter reading is 0.1 ampere. So great. So he's saying in this branch, you have a current of 0.1 ampere. The voltmeter is reading 12 volt. So the voltage across the resistance plus voltage across the ammeter is 12. That is given in the question. And the current is 0.1 in the branch. So 0.1 into resistance plus 0.1 into ammeter ka resistance, which is RA, must be 12. So R plus RA is 20 is equal to 120. Therefore, R is equal to 100. So there's nothing there, just substitution there. All got this? You know the voltage, you know the current, so just multiply it. Again, if you see, questions are not difficult, but when people see ammeter or voltmeter, they think you always have to use that formula. Not necessary. So this 12 volt is across resistance plus ammeter. Are you getting it? So 12 volt is not across the resistance. The current is same in both the resistance and the ammeter because they're in series. Any doubts on D and D? This G, right? I'll change the question, okay? So we have 4 devices like this. Arrange them in descending order of resistance. That's a much better question. Meaning, you have 4 devices: ammeter 10, ammeter 5, voltmeter 5, voltmeter 10. So you have to tell me which will have a biggest resistance, then the second, third, and so on. Arrange them in descending order of resistance. The first one is a pretty good, CD question. Like, so someone wants to verify Ohm's law. What is Ohm's law? V is equal to IR. Then how should I connect the voltmeter and ammeter? Hmm. Right, Param. Look at F part, okay? So to verify Ohm's law, we need to use V is equal to IR. right? So voltmeter must be in parallel. This thing we wrote before. Ammeter in series. So now see which one is in parallel, which was in series. B option. Make sense? G is a good one. G should put a star or something for this. It's a really good question. So I gave you four devices: an ammeter of 10, ammeter 5, voltmeter 5, voltmeter 10. Between these four, who has the biggest resistance? Who is the second? Who is the third? And who is the last? Right, Utsa. Hmm, right, Samyak. Try, others try. I'll give another 30, 40 seconds. Think about it. Listen, this is the in F, why not C? C में देखो ना क्या होगा? Voltage is right, but is the current in the ammeter same? Is the same current in resistance? Current should be same, no? You should measure the current in the resistor and voltage across the resistor. Listen to the G part, everyone. The first thing, between an voltmeter and an ammeter, who has big resistance? Voltmeters are big resistance, isn't it? That is the first thing. Between an ammeter and an voltmeter, देखो ना यहाँ पे if you see the logic also, an ideal ammeter will have zero resistance. So ammeters generally have very small resistance. An ideal voltmeter will have infinite resistance. So voltmeters will have big resistance. So if you take any voltmeter and any ammeter, you can be sure the voltmeter will always be biggest, right? So for voltmeters, this is the idea there. So the bigger the resistance, the better the voltmeter. That was one of the precautions here. RL must be large. So for voltmeters, the larger the resistance, larger the range. So larger resistance implies larger range. So between two voltmeters, whoever has more voltage car range has a bigger resistance. But for ammeters, it is reverse. The shunt resistance must be small. For ammeters, the smaller the resistance, larger the range. That is the main catch there. Now, from this thing, you can clearly see. So, who is the biggest voltmeters? Between the two voltmeters, who is the biggest? The 10-volt guy. Then the second voltmeter, 5 volt. Now, between the two ammeters, 10 and 5, who has the bigger range? 10. That means that resistance must be the smallest. Is that making sense? Between the two ammeters, whoever has more range will have small resistance. So that means A is the least of all. Between the two voltmeters, the bigger one will have the bigger resistance. D is the biggest one. So DBCA. Is that clear, everyone? That is a much better question than asking which is the biggest. All got this? Let's get two more. Yeah, this is an easy stuff. Let's get this. Okay, let's see. The first was easy. Just now I told you an ammeter should have small resistance. True. Voltmeter should have large resistance. True. A and D is the answer. I is again another good question. You took an ammeter and voltmeter, both are non-ideal. So they will actually take some current. Then what is the value of the resistance? You can see all the questions, right? They're like 2 to 3 steps ka things like, so that's the thing there. Okay, listen to this catch. I'll show you two different models in this also. So in this case, first of all, we have an ammeter here. We have a resistor here. We have a voltmeter. Now understand this. The voltmeter is supposed to measure anything in parallel. So here we get the voltages right. But look at the current. The current, this is showing you 4 ampere. So some current the voltmeter will take. So the resistance is actually getting 4 minus I. 4 ampere is not flowing in the resistance. It is 4 minus I. Therefore, resistance R is nothing but voltage across the resistor, which is 20, which is true. Current in the resistor is 4 minus I. This value is greater than 5 ohms. Are you getting the difference? Because the voltmeter is non-ideal, it will take some current. So this ammeter is not measuring current in the resistance. It is measuring current in the resistance plus the voltmeter. Are you clear? And in the Ohm's law, V is equal to IR. V is the voltage across the resistor. I is the current in the resistor. Now, there's another way you can do this thing. You can keep the ammeter and resistance together, and you can keep the voltmeter across this. Now, this is a different question. Now, what do you think? The ammeter, if it measures 4 ampere, meaning same current will flow through this. But the voltmeter, 20 volt, is actually measuring voltmeter across ammeter plus voltage across resistance. So resistance will be 20 minus VA by 4. So this will be less than 5 ohms. You're getting the problem here? So if you want to measure the resistance of a thing using voltmeter and ammeter is not a good idea. No matter what you do, you'll always get an error. So for the given case, C is the answer. So if I try to adjust the ammeter, voltmeter goes off. If I try to adjust the voltmeter, ammeter goes off. One of them will always create an error. So to find resistance using ammeter, voltmeter is not a good idea. Then how do you find resistance? That's where our second device comes, a meter bridge. We call it meter because we use 1 meter ka wire. So a meter bridge is basically, it is used to measure resistance using principle of Wheatstone bridge. So this is based on Wheatstone bridge concept. The concept is pretty straightforward. So the setup would look like this. We have some metal frames. So between these two joints here, you connect a resistance wire. So this black thing is a wire with uniform resistance. Let the resistance be R naught and length L. Generally, the length will be 1 meter. I'm just taking L. It can be anything else. And the idea here is in these gaps which you have, you connect a resistance. So let's say this is Rx, which is your unknown resistance, which you're trying to find. And here we have one more resistance, R known. So this is a known resistance. And this is connected to a battery. And here we have the galvanometer is connected from the middle with a needle like this. This thing here is called a jockey. So that arrow kind of thing is called jockey. So this jockey, right, can be moved. So that arrow ka tip thing, it can be dragged on that wire. The jockey which can be moved. So that I'll write it down here. So that arrow thing which you're seeing, this is called a jockey. So you can drag this on the wire. So this is how the experiment starts. So you put the setup here and you keep moving the jockey. As you keep moving the jockey, at some point, the current in the galvanometer becomes 0. This is X and this is L minus X. So when this happens, we keep moving the jockey till Ig becomes 0. So when this happens, this is the word they will use. They will say bridge is balanced. So if they say bridge is balanced, meaning the current in the galvanometer is 0. Or if Ig is 0, it is called as bridge is balanced. इतना तक story clear है? What is happening? So now if you actually draw the circuit back again, this is how the whole thing will look like. So indirectly, this is just two resistors. This is that wire there. This is the galvanometer with the jockey there. And this is your battery there. This was X and this is L minus X. This is your Rx, this is your R, and the current in the galvanometer is 0. You can clearly see this is looking like a Wheatstone bridge. The current in the middle resistor is 0. Since it is a Wheatstone bridge, then the resistance will be Rx by this resistance is this resistance by this resistance. Remember? That ratio must be same. So the wire resistance will be R naught by L because R naught is the total resistance and L is the length. So R naught by L into X is equal to the known resistance R by R naught by L into L minus X. Just divide them and you'll get Rx is equal to R into X by L minus X. I'll do one thing. I'll just call it X. That will be confusing again. I'll just keep it as Rx only. There, that's your formula there. So the resistance of that unknown thing will be Rx by L minus X. Direct formula. So you keep moving the jockey. At some point, you'll get a resistance. Let's say X is equal to some 40 centimeters. Substitute there, you'll get the resistance. Is the experiment clear, everyone? Is the setup clear? So you will keep one unknown resistance here. We'll keep a known resistance here. So this wire is acting like two resistors. By moving the jockey, you're changing the value of this resistance and this resistance. So as you keep moving the jockey, at some point, the ratio will balance. At that point, we say the bridge is balanced and the current in the galvanometer becomes 0. If the current in the galvanometer becomes 0, meaning this has become a Wheatstone bridge. If this becomes a Wheatstone bridge, then this ratio by this ratio must be equal to this by this ratio. You know capital R, you know X, and you know L, you know everything. And once you keep there, you're done. So few things you have to take care while doing this. The balancing length is independent of cross-section area. So that black wire, it can have any thickness. It doesn't matter. It depends only on the length there. So balancing length is independent of, so you'll get questions like this. What happens if you replace the wire with a thicker wire? Nothing happens because it's a ratio, na? R naught by L will always cancel. Is independent of area of cross section of the wire. Second thing, if length of the wire is increased, so instead of using 1 meter wire, if I use 10 meters wire, we get more precision. Basically, you get a much more accurate result. Right? Meaning, for example, if you have 100 volts across 1 meter, then you get 0, 1, 2, 3, right? If you have 100 volts across 10 meters, you'll get even smaller voltages. Like the number of divisions will be much smaller. So in the jockey, we use a resistance box. Yeah. Technically, this is what I showed you with the wire and all. But later on, we will see something called a post office box. The picture actually ऐसा दिखेगा. So you will have some device kind of thing like this. Instead of a wire, we'll have this. We have plugs and switches and all. You can, rotate them. You can push them, and the resistance will change. So something like that. So we will check it out. For the 2 ohm it was 85, for 3 ohm. Yeah, there is also some errors in this, which we'll see in the next class. So what happens now? Even though we are saying the length of the wire is L, think about it. In order to connect this wire, we will use some wire to connect it. No? We will need some more extra wire to connect it to the circuit. So that actually creates an extra length here on both the sides. So it does have its own errors. Yeah, but better than using voltmeter and ammeter. But everyone got the idea of this? It is a simple Wheatstone bridge. More about this in the next class we will discuss. And next class we will also do something called potentiometer. That's the most important thing. Yeah. Next class we will wrap up the chapter. So we will be done with this. Maybe if time permits a bit, we will start off with the introduction of ray optics. But next class we will wrap up this thing. So
Sir, there is an infinite resistance section in the post office box.
yeah.
Sir, what is that?
When I teach you, I'll tell you.
Then is it not there in this chapter?
So that is a thing there. So any doubts, anything else, please stay back and ask. Then, or else you're free to leave. I'll see you again on Thursday. We'll continue from there. And those who have doubts, you stay back. We can discuss.